Please just close the box and then we can get started.
Close the box.
The box. On the right.
This box.
Yes. Okay.
Oops. What was that?
That went.
Click on the lower bar on the Zoom thing.
I reclaimed host. We had an issue before where I wasn't host and the Zoom call died. So
Okay.
That was my fault.
Okay, but it's all good now, Lawrence, right? Okay.
yeah, all good.
Okay, thanks very much. Welcome everyone to this graph-themed DSDSD. I'm going to talk about the LDBC social network benchmark today. And just to set the stage, I would like to define what I mean by graph databases. This is going to be a broad definition that incorporates all sorts of graph data management. So we talk about what a potential graph data model is and what graph query languages are supposed to be do at the very minimum. And one potential data model that is very popular recently is the so-called property graph data model. We can see that this is clearly a graph of nodes and edges, but these have labels, like the nodes on the top are called tags, the nodes at the bottom are called persons, and also we have edges between them, like the tags have subclass of relationships and the people have node relationships. Also, both the nodes and the edges can have a number of properties, like the people have names, birth years, and when they get to know each other, we add a singed attribute to those edges. And one question that comes up quite frequently is that everyone has studied graphs in their undergraduate course, and it's interesting to see how they relate to this graph. Well, parts of the property graph form classic graph data structures, like the hierarchy of tags is a tree, the graph of the people is a network, and this connection between a person is interested in a certain tag forms a bipartite graph. So this is where traditional graph theory is connected to this. But usually users don't use traditional graph theory. They're more interested in issuing graph queries. For example, we have this person, Bob, and Bob may be interested in some sort of an art topic, but regrettably, Bob doesn't have any immediate friends who are interested in art. So we use the power of graph queries to help Bob. And we formulate a query in Cypher, which is a popular graph query language, and you can see the query above. The query says, we are interested in shortest paths that start in Bob, do an arbitrary number of hops, and then they end in P2, which is another person. And that person in turn is then interested in some tag that is a subclass of art. And you can see that this is a pretty concise way of expressing that we are interested in shortest path problem and a tree traversal problem. And we also do a join among the interested, along the interested in edge. So if we run it, the system will then return this path to us, and it may even visualize this for us. And I think this example demonstrates the three key tenets of graph data management systems: some graph data model where we can argue about our data in terms of nodes and edges, some graph query language which allows a concise way to formulate pattern matching problems and pathfinding problems, and visualization that allows us to see what we are actually querying and what we are getting back from the system. And this became very popular in the last decade. So we have now a bunch of graph data systems in various categories. One popular category is transactional systems like Neo4j and Amazon Neptune. There are also more analytical systems like Tiger Graph, Relational AI, and Oracle PGX. But also we have graph search engines like Travaras. If someone could please mute
Jim, I think.
someone. So someone is clicking in the background. Please check whether I'm muted. Thanks. So Travaras is a graph search engine. It's kind of easy to think about it like a Spark for graphs. So it's not necessarily a database management system. It's a query engine on top of a snapshot of graph data. So this is all good and well, and users seem to like these systems, but regrettably, graph data management systems have serious performance problems. And this is not a secret. This year at EDBT, Peter gave a keynote titled "The Sorry State of Graph Database Systems," and it is indeed the consensus that these systems have much to improve regarding performance and maturity. And I believe this should rather happen really fast. Otherwise, these systems will just fade into obscurity because users get bored with their problems. How can we help facilitate that evolution? Well, one idea is to take the successful blueprint of the TPC, the Transaction Processing Performance Council, which stimulated competition among the RDBMS vendors. And it did so by setting clear goals to compete on, clear rules, which govern the competition, and also an auditing process which governed that this is done in a clean manner and people don't cheat or use special features for their benchmarks. And you can see the result on the right. Over the course of 15 years, they have improved relational performance for transaction processing roughly by 1000x. And I think this is a really enviable thing, and I would prefer if this happened to graph data management systems. So roughly 10 years ago, the LDBC, the Linked Data Benchmark Council, was set up as a collaboration between industry and academia with the plain goal of accelerating progress in graph data management systems. The method that LDBC uses is it creates standard benchmarks and then supervise their use. And it's very important that LDBC takes a neutral stance, so it's not particularly biased towards any data model, any hardware, any architecture. We believe that we just give the standards, govern their uses, and let the competition decide what the winning technology is. One of our most important benchmark suites is called the SNB. This is the one that targets property graphs and graph query languages, and it stands for the Social Network Benchmark Suite. Surprisingly, its dataset is a social network. We choose this because it's something that's very easy to understand and captures interesting graph problems. So you have already seen parts of it, like the tags and the person knows person network, but there are other parts of the graph. We have forums where the persons post messages and create message threads for discussion, similarly to Twitter, Reddit, and other systems. And one of the interesting features of this graph is that it's full of correlations. It has structural correlations. For example, if two people share an interest, they are more likely to become friends, or if they attended the same university, they again are more likely to become friends. But it also has attribute level correlations, like people in France are more likely to have a French name, etc. And one particularly interesting and hard thing that this data generator of LDBC does is that it creates a temporal graph. To do the temporal graph, we use the approach called lifespan management. Basically, what this entails is that the generator, when creating the graph, sees the entire temporal graph at once. So it sees back into the past and forward into the future. When we create a node, we can tell when that node is going to be deleted from the network. And the challenging thing is that we have many implicit constraints that we need to enforce while doing this generation. For example, person pers wants to post into this forum F in this small example. To do so, the person first has to become a member of this forum. So what we do with our lifespan management is that we first say that to become a member of a forum, both the person and the forum have to exist. So we intersect the intervals and select the possible area where the person has a chance of becoming a member of the forum in the first place. Then we select the beginning and the end of the interval and carry that over for the rest of the computation. When we have that interval of the has member edge, we select the posting time from the beginning of that interval until the end of that interval. And this is kind of a recursive problem. So if you want someone to reply to the middle of a message thread, it's kind of challenging to find a slot where that message can be posted. Another challenge here is that these random generations, when we click the blue nodes on the interval, are anything but uniform. We have many flash mob events where there is a big concert and then people start to post around that time and around that place quite a big number of messages into the forums. And this, of course, makes for interesting optimization problems when querying these graphs. So if we apply these and create a temporal graph, what we end up with is this big temporal graph that we then chop into little pieces. The first piece is the initial snapshot, which is usually 35 months of data. And then the rest is chopped into daily batches. And the daily batch is, here is your number of inserts that you need to apply on this day, and here's your number of deletes that you need to apply on this day. And these deletes can be quite heavy because of all the recursive effects. Even something as simple as deleting a small forum, which is just one operation, can result in 20 plus deletes, as demonstrated on these slides, because it deletes everything which is underneath the forum. Deleting a person can easily result in deleting 5,000 to 10,000 entities, so it's quite a heavy hitting operation to the database. One benchmark that we have recently worked on is called the SNB Business Intelligence. This is analytical in nature, and you can think of it as a graph OLAP workload. Basically what it does, as I mentioned, we take 35 months of data for the initial load. Then we have 33 batches of write and read operations. And the way we structured with this benchmark was that we first do a power test, meaning we apply 1 day's worth of update, then run all our queries sequentially. This serves two purposes. We can validate their correctness, and we can also gauge their individual runtimes. And once this block is done, we just go free for all and allow the system to consume the updates and run the reads concurrently. So then the system has a lot of tricks that it can pull regarding the scheduling of these operations. One challenging thing is ensuring that we do not just run the same queries over and over and over again. To this end, we do something called parameter curation. This technique is especially important for graphs because graphs are heavily skewed and correlated, meaning that if you have a query like this, when we discover some messages in the two-hop neighborhood of a given person, it's paramount to select a person that guarantees some sort of stable, predictable runtime. What do I mean by this? I mean that if we uniformly randomly select and we just select a person who just joined the network and has 2 friends versus if we select the Justin Bieber supernode in the graph, then it's going to be 2 very, very different queries with orders of magnitude in difference in terms of their runtimes. So this is, of course, undesirable. The other typical graphy problem is that if we select 2 people, look for reachability, and we select 2 people where there is a path, which is usually very easy to find, or we select 2 people where there is no path, which is much harder to prove for the system. So this is, of course, very undesirable, and we need to do some tricks. Let me demonstrate what the effect of this parameter curation is. In purple, you can see the runtimes of uniform randomly selected parameters on a small scale data set with Umbra. And you can see that in all of the cases, it's a very wide distribution. It has many random knots on it, which are like modes. There are massive gaps in it. So if you just run maybe 5 to 10 queries, it's very hard to reason about the performance of a system because the results can be all over the place. The solution that we propose is that we select nodes and ranges so that it's balanced out and ideally results in somewhat like normal distribution. You can see that the green curated runtimes are significantly better than the purple ones. They are much narrower and have less gaps. They are still not perfect, but we believe that this is now sufficient for ensuring somewhat predictable runtimes. I would like to demonstrate 4 queries in this presentation, which all stress some sort of interesting feature. The first is the presence of worst case optimal joins, which is a new technology in relational data processing that ensures that cyclic subqueries, like this triangle of people living in the same city, can be run efficiently. This query is easy from a parameter selection point of view because we just select big countries, which kind of push the runtime a bit up. And we select similar time intervals when the persons got to know each other. A more challenging query for parameter selection is this correlation query. Here we find 2 countries like France and Spain, and we check whether the people who live in these countries and know each other interacted at all, and if so, how many interactions did they have with each other? And here we can play on the strength of the data generator that it has these correlations baked in, and we have 2 variants of the query. In A, we select close countries, which result in much higher runtimes. And in B, we select countries like France and New Zealand, which result in very small runtimes. So there is a massive difference to be made based on the proximity of the countries. Next is another query which triggers the factorization representation technique that is also quite novel. This is based on the Twitter Who to Follow paper, which says that we should do diamond-shaped queries to say that you should follow US person 1, should follow this other person 2, because you share an interest and also have many mutual friends, making it likely that you will find what the other person posts find interesting. The trick here is that we are not interested in the interim persons individually, we're just interested in their count. And if you use a factorized representation, you can get away without actually enumerating those people, and counting them becomes a much simpler operation. And finally, this is, of course, easy parameter generation-wise. Finally, there is a path query, which is hard parameter generation-wise, because what this entails is a recruitment query. So we are company 1, and we want to hire person 2, but we have no direct connection. So we want to build this trusted path towards person 2, which means that you take the same university edges, people who have studied at the same university, weigh them based on the class year. If you studied in the same year, that's weight 1. If you studied 9 years apart, that's weight 10. And then on that, we compute a weighted shortest path. Now, this may sound like a very sparse graph, because what are the chances that 2 random people attended the same university? Well, because our generator is correlated, it's actually roughly a 10–15% chance. So this is a pretty dense subgraph of the original graph. But still, it's hard to ensure that there is always a path between some employee of the company and the person 2 that we selected. And to this end, we use quite a convoluted parameter selection technique, which is that we pre-compute the same university nose edges during the measurement window. So the people and the nose edges who are there in that 32-day period when we benchmark. Then we pick similarly sized companies, and then we only return person 1 and person 2 pairs where there is a path between some employee and the person 2. And this, of course, implies that we practically have to do the query during generation time in order to then ensure that the runtime is somewhat predictable. So parameter selection is quite a big feature of this benchmark. Overall, we are quite happy that we now have 3 complete reference implementations, one in Neo4j, another in TigerGraph, and the third one in Umbra with collaboration from the folks at TU Munich. Okay, so why is this benchmark so complicated, and what decisions did we make to prevent misuse? One thing that we noticed is that people prefer to use benchmarks as a sign of maturity and say, my system can do the LDBC S&B benchmarks, so it is a mature, scalable, industry-grade system. But of course, we are happy if this is indeed the case, but we want to prevent people from having immature systems marketed as mature systems with LDBC. And by signs of immaturity, we mean that we encounter many systems with an append-only storage or read-only storage, a very limited data model that only does int64s, or a basic optimizer that doesn't detect any sort of join order that it should. The solution to these immaturities in the benchmark is that we use large-scale data sets, which themselves break many systems just by the sheer amount of data that they should load. Our data is quite interesting, meaning it's not just ints and ASCII strings, it has dates, arrays, Unicode strings, etc., which is quite a challenge even today to many systems. And we have complex queries with roughly 30 choke points, which all encode some sort of challenge that the system should deal with during optimization, storage, or execution. And one thing that is quite challenging, and it turned out to be more problematic for these systems that we thought, is deletions. Many systems don't support deletions, or they have trouble finding the nodes that they should delete, or they delete, but they lack garbage collection, etc., etc. So it's quite an interesting finding that deletion is this hard in graph data management systems. The next step in preventing misuse is to try to avoid benchmarking mistakes and also cheating. The technique that we use to this is purely organizational in nature. We have an auditing process where we have a third-party auditor who inspects the code, reruns the benchmarks, and then writes up a full disclosure report for reproducibility. We have audited results on ldbcouncil.org. It seems that companies are now interested in getting their systems audited, which is great. And if they don't want to get audited, then of course they should not claim that they have audited results. And to this end, we have now trademarked the LDBC term. So any benchmark that is non-audited requires a disclaimer that this is not an official LDBC benchmark. That said, we still encourage people to use LDBC with the disclaimer because we believe that you can derive interesting results even if you don't implement the full benchmark. So to sum up, LDBC is this 10-year venture of trying to define a standard benchmark for graph data systems. It started with the data generator in 2012 and had 2 benchmark papers on the SNB with the current BI paper coming out soon. We had many user community meetings to stay relevant and stay in touch with the community. The next one is going to be in Philadelphia as a 2-day event co-located with Sigmod. So you're welcome to join us. And we're also working on other benchmarks. There is an updated version of the SNB Interactive, which is done by David Peroja, who is here today. And there is the financial benchmark, which is led by the End Group, and it's more like a distributed, concurrent, low latency, query-focused transaction on financial graphs. So those are our flagship benchmarks at the moment. And if you're interested in trying them out, or if you are using them, please let us know, and we are happy to chat. Thank you.